All right, we're going to tackle examples 4 and 5. These ones are a little bit more difficult in that they incorporate POH. So if you haven't read anything about POH quite yet, maybe skip this video until you have read about POH and how it relates to pH. Otherwise, let's dive in. So example 4 says, calculate the pH of a solution made by dissolving 1.25 kilograms of sodium hydroxide in enough water to make 1,000 liters of solution. So I'm going to start off by writing the dissociation equation for sodium hydroxide. Sodium hydroxide is a strong base, so it completely dissociates into sodium ions and hydroxide ions. So pH, if you recall, pH is looking for the is really the negative logarithm base 10 of the hydronium concentration. Now in this example, I don't have any hydronium in here, and but that's not really all that big a problem, because if you read about POH and hydroxide ions, you'll realize that they're kind of the flip side of the coin to pH and hydronium. These two entities, hydronium and hydroxide, are two sides to the same coin. And in fact, if we know one, we can easily determine the other. If we know pH, we can easily determine POH through a very interesting, beautiful, and elegant relationship. So anyway, let's go ahead, and what we're gonna do is find the hydroxide ion concentration, and then I'll show you how we can work our way up to pH. So we start off with 1.25 kilos of sodium hydroxide. So 1.25 kilos, I should turn that into grams, so that'd be 1,250 grams. Volume is going to be 1,000 liters, so that means my concentration of sodium hydroxide is going to be moles per liter, so I need to do 1,250 grams divided by the molar mass of sodium hydroxide. And sodium hydroxide is sodium, 22.99, plus hydrogen, plus oxygen. So we get 31.25 moles, and we divide it by our volume, 1,000 liters, and we get that value there. So I'm going to record the whole number, knowing that I'll eventually round to significant digits at the end. So here's my value for my sodium hydroxide concentration. Sodium hydroxide dissociates 100%, so we can actually take that same number, and because it's a 1-to-1 ratio, I can say my hydroxide ion concentration is the same thing. All right, so there's my hydroxide ion concentration. I cannot directly calculate pH from the hydroxide ion concentration. Instead, what I can directly calculate is POH. And POH, like pH, is a negative logarithm base 10, but this time it's the negative logarithm base 10 of the hydroxide concentration. So as long as I know my hydroxide concentration, I can plug that value in, apply it to this formula, and that'll help me find POH, or the exponential power of hydroxide. So I'm going to do negative log 0.03125. And that gives me a POH of, let's see, I have 3 significant digits, so I should have three digits after the decimal, so 1.505 is my pOH. Now, how do I find the pH? Well, the relationship between the two is that pH plus pOH is always going to be equal to 14. So 14.00. So if I know my pOH, I can actually find the pH by taking this number and subtracting it from 14. So I'll take that number, plug it in there, and from this I'll calculate my pH. So pH is going to be 14, subtract that number, and I should still have three digits after the decimal in my final answer for pH. So I'm going to do 14 subtract the number, and I get a pH of, what do we get here? 12.495. And there you go. So this is a really helpful relationship. I'll kind of derive it next year, and if you take Chemistry 30 or grade 12 chemistry, I'll show you where we get this from, but it's a really useful relationship right now, and helps us convert between pOH and pH. All right, last example is example 5. So this one has just an extra wrinkle in it, but we're actually only being asked to solve for the pOH of a solution of barium hydroxide. So let's go ahead and figure that one out. The nice thing about this one is we're going to find the wrinkle right away. And we find it by writing our dissociation equation. So barium hydroxide is going to dissociate to form barium ions and hydroxide ions. But if you're paying attention, in the formula unit for barium hydroxide, I have 2 hydroxide ions per 1 unit. So that means I need to write a 2 here. So for however many moles of barium hydroxide that are dissociated, I make 2 times that amount of hydroxide. Barium hydroxide is a strong base, so we can assume 100%. Remember, our calculations here are dependent on these being strong acids and bases, so they don't work if these are weak. So pOH of a solution of barium hydroxide, okay, if I've got 0.5 grams of the solid, and I need enough water to make 375 mils of solution. So I've got 0.5 grams, and I need to make 0.375 liters of solution. I should find the molar mass here, capital M, molar mass of barium hydroxide. It's going to be barium's a big boy, 137.33, plus I have 2 hydrogens, so that's going to be 2.02, and I have 2 oxygens, so that's going to be 2 times 16 is 32, and I get a molar mass of 171.35. grams per mole. So let's go ahead and calculate our concentration of barium hydroxide. So that's going to be 0.5 grams multiplied by my conversion factor, which is the molar mass. And I divide it by my volume, like so. And I'm going to get a number out of here. divided by 171.35 divided by 0.375. So if you're following along, you should get a number like that. So I'll just round it here. That's what, 7.8 times 10 to the 1, 2, 3. Moles per liter. Now here's where our wrinkle comes in. Comes back to this hydroxide. For every 1 unit of barium hydroxide, I make 2 of hydroxide ion. So what this means is that my concentration of hydroxide has to be 2 times the concentration of barium hydroxide. Like that. So I'm going to take this number, multiply by 2, and that gives me my hydroxide concentration, which is great. Because now I can, once I have hydroxide concentration, I can calculate the pOH, which is the negative logarithm, base 10, of the hydroxide ion concentration. So the important thing there is to multiply by 2, because I make 2 moles of hydroxide for every 1 mole of barium hydroxide. So let's go ahead and find out what that is. So I'm going to do 2 times this number. Okay, and then to find my pOH, I take the negative log of that number, and I get a pOH of, let's see, I only have 1 significant digit there, so I really only should have 1 digit after the decimal place. So I'm going to have it as 1.8. pOH is 1.8. So might be a good time here to just kind of remind you, if you read this in the reading, great, and if you remember, that's even better. But if we have, here's our pH scale. That's 7, 0, 14. That's pH. The pOH scale is the reverse. It's actually the opposite. So if you have a pH of 14, that's going to correspond to a pOH of 0. So the pOH scale actually, just like the pH scale, except it's going in reverse. So if you've got a really high pH, that means you've got a really low pOH. If you've got a really low pH, it means you have a really high pOH. Something that's neutral will have a pH equal to the pOH. So this is a really useful relationship, and kind of like if one's high, the other one has to be low, vice versa. And that comes back to like why we can use this conversion here. For these both to always equal 14, that means if there's an increase in one, there has to be a decrease in the other. So yeah, that's how the two of them go hand in hand. Really, really basic things up here with pOHs close to 0 will have pHs around 14. They're going to have really high pHs. Really acidic substances with really low pHs are going to have really high pOH values. So this value here is a pOH of 1.8. That puts it right about here. A pOH of 1.8 tells us that we are very much still basic. So these scales are drawn up right beside each other. Doesn't matter. We're still at this is still the basic part of the scale. And then on both scales, this is the acidic part of the scale. So if you have a pOH that's between 7 and 14, that means you're acidic. All right, so that's it for this video. See you in the next one.